This is going to be our last video on the techniques for solving lights out problems. In this one, we're going to look at linear algebra. So at the beginning, we're going to just review the rules of lights out on graphs, just in case you've forgotten. We're going to talk about reducing the problem of winning a lights out game to solving a system of linear equations. And then we're going to use some of our knowledge from linear algebra to figure out when a solution exists. All right, so we're going to actually give some proper terminology to our lights out games. The lights out game we've been looking at in this one is called the neighborhood lights out game. And it's related to the neighborhood matrix, which we'll see later in the video. But the neighborhood lights out game, when it's played over ZK, is played as follows. We start off with labeling the vertices of G with labels in ZK. We play the game by toggling the vertices. Each time we toggle a vertex, that's going to change the labeling. When we toggle some vertex V, we increase the label of each vertex in the closed neighborhood of V by 1. And what I mean by the closed neighborhood of V is V plus any vertex that is adjacent to V. And then we win the game when every vertex ends up with label 0. So we're going to talk about a new strategy for winning a lights out game. What we're going to do is, well, here's an example, a graph that we're going to look at. This has 7 vertices, V1 through V7. And the edges are given by the lines in between those vertices. And we're going to say, we want this to apply no matter what the initial labeling is. So for each VI, we're going to say the labeling of that is BI. So for V1, it's B1. For V2, it's B2, etc. Now, we're going to be a little bit careful about hitting the buttons. We're not going to commit to a number for each vertex. We're going to just say that xi is the number of times we toggle vi, and then sort of at the end, we'll see if we can figure out whether we can tweak those xi's so that all the labels are 0. And each time we look at the problem, we're going to look at the vertices individually to see what their final label is, put all that information together to see if we can make all those final labels equal to 0. So we'll start by focusing on V1. Now V1, its initial label is B1, and we want to end up with a label of 0, and we want to look at which vertices are going to affect what that label is. Well, every time we hit V1, we increase the label by 1. Every time we hit V2, we increase the label by 1 as well. That means when we hit V1 x1 times, that increases the label by x1. And when we hit V2 x2 times, that increases the label by an additional x2. Altogether, that's x1 plus x2. Now, when we increase it by x1 plus x2, we want to cancel out that b1, which means that we want x1 plus x2 to be equal to negative b1. We're going to do the same thing for V2. We start off with a label of B2. That label is going to be changed by when we toggle V1, V2, and V3. The total amount we change it is x1 plus x2 plus x3, very similar as we did before. We need that to cancel out the initial label B2, which means that x1 plus x2 plus x3 has to equal negative B2. For V3, it's going to be very similar. We start off with a label of B3. That one gets changed by V2, V3, V4, and V7, which means it's going to be changed by a total of x2 plus x3 plus x4 plus x7. That has to cancel out the B3, so we set that equal to negative B3. V4, same thing. Start off with label B4. It's going to be affected by V3, B4, V5, and V6. We get that as its the amount that it gets the label gets increased by, and we set that equal to the x3 plus x4 plus x5 plus x6 equal to negative b4. For v5, very similar. Initial label b5, labels changed by toggling v4, v5, and v7. Then when we cancel out b5, we end up with x4 plus x5 plus x7 equals negative b5. We keep on going. We end up with x1 plus x2 equals negative b1. x1 plus x2 plus x3 equals negative b2. There's our third equation. our fourth equation, fifth, sixth, and seventh. We get 7 different equations for that. They all have to be true in order for the final labels to be 0. And I know what you're saying. That is a system of linear equations. And if we want to look at what the matrix equation looks like, well, there it is. And so we can solve that using the methods that we used to solve systems of linear equations back in the old days. It's going to be a little bit different because we're looking at our numbers being in zk instead of like the real numbers, but otherwise very similar. So we can solve this as in linear algebra. Remember, our computations are in zk, so that's going to somewhat affect our elementary row operations when we're doing row reduction, for instance, and other things like that. All right, so let's look at this more generally. So how do we win a given neighborhood lights out game, if that's even possible? Well, here's one way to do it. Again, if possible, might be impossible to win. Order the vertices however you want, v1 through vn, where n is the number of vertices. Let bi be the initial label of vi, and then we're going to toggle each vi xi times. Right? Again, we're leaving the xi as a variable because we want to make sure to adjust them at the end so that they work out to give all our labels 0. Now, when we finish doing that, our final label for each vi is going to be bi plus all of the ways that it gets changed by toggling vi and its adjacent vertices. And the way I'm going to express that is like this: the sum of cij xj. Now, if vj is adjacent or equal to vi, then we're going to be increasing that by xj. So the cij in front of that xj has to be 1 to make that xj. But if it's not adjacent, we want the cij in front of that to be 0 so that it doesn't contribute anything. So that's another way of saying that is we just let cij equal 1 when either I and j are equal or vi, vj are adjacent, so they form an edge in the graph. And if that's not the case, then we set cij equal to 0 because we don't want that xj to contribute to the label of vi. So if the matrix for that equation is going to be n equal to all the cij's put in a matrix. And that actually has a special name. It's called the neighborhood matrix of G. And if you look at the definitions of the cij's, they look very similar to the definitions for the adjacency matrix. And in fact, n is exactly the same as the adjacency matrix, except for since I can equal j for it to be 1, you get 1s down the diagonal. And we win the lights out game precisely when nx is equal to negative b. And that means if we let negative b be any labeling that we want and be able to win that, the only way we can win every single game is when n is invertible. So we took this lights out game and converted it into a question of whether a given matrix that is completely determined by the graph is invertible. So I want to sort of leave you with a definition that we've been kind of hinting at throughout these videos, but I wanted to make a bit more explicit. And that is the notion of an always winnable graph, right? So, and whether or not we can win the graph depends on both the matrix in our equation, but it also depends on the number of colors that we have as well. So when we talk about always winnable, it's going to depend on the matrix n and the number of colors k. So we say a graph G is nk always winnable, or if we want to abbreviate it a little bit, nkaw, if the neighborhood lights out game can be won for every possible initial vertex labeling of G with labels in zk. And as we've seen, that's going to happen precisely in the following situation. It's going to be nkaw if and only if the matrix n is invertible over zk. So that gives you an idea of some of the methods that we use in these. We don't necessarily have to study this in our project for the neighborhood lights out game over graphs. There are some other ones that I have too, but a lot of them are going to use very similar strategies for coming up with theorems.